Okay, we've been talking about atoms, and we've discussed various models of the atom. For example, Thomson's plum pudding model, Rutherford's solar system model, and I introduced to you the Bohr model of the hydrogen atom as well. And I wanted to look a little bit more closely and quantitatively at the Bohr model today. Because it's nice to take this part nice and slow, so I want you guys to be able to take your time with this, because the algebra is kind of intense. So let's do this nice and slow, and let's do it together, most importantly. Just to remind you of what the Bohr atom says. Number one, it assumes that the electron, it's kind of like it's semi-classical in the sense that it's kind of like Rutherford's solar system model, because it assumes that you have a heavy nucleus, which is like the sun. In this case, it's a proton, and an electron going around that nucleus, like a planet going around the solar system. So that's the first assumption in the Bohr model, that these electrons are going in circular orbits. The second assumption, and this was the very weird one, this was the sort of quantum addition to the Rutherford model. Bohr said that the orbits, the only allowed orbits in, for example, a hydrogen atom or any atom, are those for which the angular momentum is quantized. You can only have quantized values for the angular momentum of the electron. In principle, the angular momentum has to be an integer multiple of h over 2 pi. Okay? So that was the second, and that's the sort of the bizarre one. The third one is that there's no radiation of electromagnetic waves for an electron that's sitting happily in one of these allowed orbits, right? That fixes the Rutherford problem of having the electron spiral into the nucleus because it's losing electromagnetic energy because it's accelerating. The only way for an electron to emit a photon, or an electromagnetic wave, is if it goes from a higher energy level to a lower energy level, right? It will absorb electromagnetic energy if it goes from a lower to a higher level. So it's only these transitions between energy levels that give us, that either emit or absorb radiation for one of these Bohr atoms. Okay, so those are the assumptions. Now let's look at this quantitatively now. So let's say that I've got a proton. So there's my proton, and here's my electron. And again, Bohr said that this electron, we can think of that going in a circular orbit about the proton. And as it does so, it must be moving with some speed, v. We know that if an object is moving in a circle, then if I were to draw a free body diagram for this electron, a free body diagram for this electron would include a force that points toward the proton. But of course we know that an electron will be attracted to the proton, so this is really nothing more than just an electrostatic force, F sub E, which in magnitude is just going to be K, Q, the charge on the electron times the charge on the proton, absolute values of each, divided by the square of the distance, right? So this is the free body diagram, and according to Newton's second law tells us that the net force, the vector sum of all the individual forces, had better give us the mass times the acceleration. In this case, the only force on the electron is the electric force, F sub E, and so that must be equal to ma. In this case, the acceleration, because this thing is moving in a circle, the acceleration is a centripetal acceleration, and the magnitude of a centripetal acceleration is v squared over r, right? And so this is how we apply Newton's second law in this situation. Now I can plug this stuff right into here, and that would look like K. The absolute value of the charge on an electron is just E, so that's an E. Now the absolute value of the charge on a proton is also just E, so that's really just E times E. Now, I can actually, with very little work, I can make this a little bit more general. If I assume that this is sort of a more general atom, maybe there's 2 protons and 2 neutrons, for example, right? In this case, it would be like a helium atom. Then the charge on the nucleus would be 2e, right? Because there's 2 protons. And in fact, if this were lithium, there would be 3 protons and some neutrons, right? So that would have a charge 3e. So in general, if we have some element with a certain number of protons equal to, call it capital Z, that's a familiar chemistry. This is the atomic number of our element, whatever it is. If we call the number of protons Z, then the charge on the nucleus would just be Z times E, right? So rather than say that this is the charge on a proton, let's call this the charge on the entire nucleus. And that's going to give me an E times a Z times E divided by R. There's an R squared down here. So mv squared over R. Okay? And now with just a little bit of work here, I've made this equation a little bit more general in that I've covered any atom that has Z protons in the nucleus and 1 electron, right? We call such atoms hydrogen-like in the sense that there's a proton and there's a nucleus and only 1 electron. So for example, if I have a helium atom and I rip one of the 2 electrons out of it somehow, leaving only 1 electron remaining, then that's hydrogen-like helium, right? And I can make hydrogen-like elements of anything. You know, if I take an iron atom and I rip out 25 of the electrons, 25 of the 26 electrons, that's going to leave 1 electron, and it's going to be hydrogen-like iron, right? There's a lab in Lawrence Livermore, Berkeley, that's making hydrogen-like uranium, for example. So that's stripping 91 of the electrons from uranium and leaving only 1 left. So you can make these really kind of crazy atoms. But there's certainly nothing stopping us with this simple model from doing, covering all of those types of atoms that we call hydrogen-like. As soon as you add a second electron here, then this analysis goes completely haywire because it just no longer applies anymore. It's no longer nearly as simple. And in fact, that's a much, much harder problem that we're not going to deal with. But we can deal with a nucleus that's got 1 electron just fine. And so I've got this equation right here. This is K Z E squared divided by R squared. And that equals mv squared over R. With a little work here, I can cancel out one of these r's, so the r kills that r, and I'm just left with this. Okay. So here's one equation. I'm going to call this number 1. Keep that on your paper somewhere. And let's go to the second piece of this. So I'll call this, what I've written over here, that's my derivation of equation 1 here. This is related to the fact that the electron is going in a circular orbit. So there's nothing too deep about that. Now, what about the second thing that Bohr told us? Bohr said that the electrons can only have certain values of angular momentum. If you remember from Physics 105, right? If I have some point right here, call it the origin, and I have a particle over here moving with some velocity like this, and say it has mass m, and this whole thing is a distance r away from the origin, then the definition of the angular momentum of this mass would be the mass times velocity, which is just the regular momentum, times r times the sine of the angle between v and r. Now, if this particle is moving in a circular orbit, the sine of theta would be the sine of 90 degrees, which would just be 1. So in this particular scenario, where v is perpendicular to r, the equation is even simpler. So I have got m times v times r. And what Bohr told us in this weird assumption that he made, he told us that the angular momentum can only come in integer multiples of h divided by 2 pi. So in fact, what I really need to do, just to be clear about this, is I need to specify these things a little bit more carefully with subscripts. So L sub n, right, is just, there's lots of different L's. There's L1, L2, L3, all corresponding to these different integer values of n. And similarly, there could be various V sub n and R sub n, right? So any orbit that satisfies this equation is an allowed orbit for the Bohr atom. Okay. So if I solve this equation for V sub n, by the way, I can look at this equation solve this equation, this stuff here for V sub n, I get NH over 2 pi m times R sub n. So here's another sort of simple relation. I'll call this equation 2. Here's sort of another simple equation that relates V sub n and R sub n. Now what I want you to do, I want you to, in a second, I want you to pause the video and I want you to take this value for V sub n and plug it into this equation right here. And the reason I want you to do that is because I want you to take these two equations and eliminate V. And that will give you, and if you solve the equation that you get for R, then you will have all of the available R values for our Bohr orbit. So go ahead and do that. I'm going to put, you should pause the video for a second and do that for yourself, okay? Okay, so hopefully you've already done this, but just to reiterate, if I plug this equation into this equation, I get k z squared e squared over r, or k z e squared over r, and that equals m, and then I want to plug all of this stuff in. So I've got n h over 2 pi m r sub n, and that's all squared, right? So then you have to just, so then it's just a little bit of an algebra simplification exercise. So what do? Well, if I multiply both sides by r sub n squared, that's just doing, I just want to kill it from this side and bring it over to this side, so I need to multiply this side by r sub n squared as well. If I do that, then I've got an r squared on the bottom and r squared on top, so these two cancel. I've got an r squared on bottom over here and an r sub n on top, so r squared over r is just plain old r. And notice also that I've got an m divided by m squared. So let me actually sort of let me go ahead and carry my squared throughout here so I don't get too tangled up here. So 2 squared is 4, pi squared is that, pi squared, and then my r squared got canceled by that guy. So I'm left with this stuff. Now let me move the kze squared down to the bottom of the other side. I can cancel one of these m's, and so I'm left with a little bit of a mess. R sub n equals n squared h squared divided by 4 pi squared kze squared m. Okay? Now, this looks like a little bit of a mess. I'm not sure what to do with that or what to make of that, but I would argue that the most important stuff in this equation are the n squared and the z. Why is that the most important stuff? Because the n is my energy level, and the z is the number of protons in my nucleus. These are the only two things that are going to change from situation to situation. All the rest of this stuff is just constants, right? And so if I factor these guys out, then I've got an n squared over z, and I've got an h squared over 4 pi squared k e squared m, where m, remember, is the mass of the electron in this case. And so all of these things are constants. If you plug these things into your calculator, I mean, these are all just constants that you know. If you plug that into your calculator, you get some number. I'm going to call that number a sub b. It's called the Bohr radius. It's often written a sub 0 or a sub b. I'm going to call it a sub b, and that's n squared divided by z, where a if you calculate that stuff out, it works out to about 5.29 times 10 to the negative 11 meters. 5.29 times 10 to the negative 11 meters. So I just did it. I derived my formula for the various R sub n in the Bohr hydrogen atom. Okay, so that was the first of the formulas that I showed you, and this is how to get it. But we can, of course, take this a little bit farther. I'm going to erase this stuff, but I'm going to leave my 1 and 2 still here. In fact, what I want to do now is figure out what the various v sub n, what are the allowed values for the velocities of my electrons in my Bohr hydrogen atom. Well, if I want to do that, I can use the same two equations, but this time eliminate r instead of v. So, on your own, once again, try this yourself first to see if you get the right answer. Solve this equation for r, and then plug that in right here. If you do that, then you can solve for your various v's, your various v sub n. Okay, do that. Okay, so when I do that, I've got my k, my z, I've got my e squared, and on bottom I've got this stuff, which is my nh over 2 pi m v sub n. And on the right, I've got my m v sub n squared. Let me bring this chunky looking denominator up here, multiply it by both sides. If I do that, then I get k z e squared equals mv squared times all of this stuff. I'm just lifting this stuff right over here. You can see if I do that, one of these, this m is going to cancel that m, and this v sub n, one of these two v sub n is going to cancel that v sub n. So I'm going to be left with, on the right, nh over 2 pi nh over 2 pi, and I've got my v sub n over here on this side. So now you can just solve this for v sub n. Feel free to stop me at any time, and if you do that, what do you get? Well, I'm running out of space here, so I'm going to erase this now. Sorry, I know this is getting a mess, but this is kind of a small board. So again, if I solve this equation for v sub n, I get that v sub n equals k z e squared times 2 pi, put my 2 pi out front, 2 pi kz e squared, and that's going to be over nh. Once again, I'm going to factor out the sort of the interesting stuff, my z and my n, and if I do that, I've got 2 pi, I've got my 2 pi k e squared over h, and that gives me a z over an n. So again, you can solve this. If you solve for this number that's just going to be some number. You can call this number v sub, this would be the speed of an electron in the n equals 1 state for hydrogen, right? Because z equals 1, n equals 1 would be the ground state of hydrogen, and so that's what this number would be. If you calculate that, you get something along the lines of about 2.18 times 10 to the 6 meters per second, and again, that's just a number times your z divided by n. So again, this is now what we've done is we have calculated the various allowed velocities in our Bohr orbit. Okay, so this was the second equation that I showed you. Now, finally, now I'm going to erase all of this stuff, and I want to do what I think is probably the most important thing. Because realistically, it is very difficult In fact, it cannot be directly done by experiment. You can't just look at a hydrogen atom and measure how fast the electron is going, nor can you really look at a hydrogen atom and actually see even how big it is, right? Both of those things are sort of beyond the means of ordinary measuring devices. It's just too small and too fast, right? But something we can directly measure very easily, just by using some light, is we can find out what the allowed energies of these Bohr orbits are. Now, how would we do that? Well, we know that the energy of an electron is going to be equal to the sum of its potential and its kinetic energy, right? In this case, the electron's potential energy, right? We've got a proton and an electron close to one another. We've actually looked at that problem before. What's the potential? What is the electrostatic potential energy, U sub E, of a charge minus E and plus ZE, right? So I've got plus ZE, and a distance r away, I've got a negative E. So what's the potential energy of this system? Well, we learned before that that's K, Q1, Q2 divided by R, which in this case would just be K times ZE times negative E. So this actually winds up being a negative number. And I've got a Z times E squared divided by R. And so my potential energy is negative K Z E squared divided by R. And my K is just what you would expect. It's 1/2 mv squared. But of course we have to bear in mind that only certain values of n, of R, and V are allowed. Those are my R sub n's and my V sub n's that I already derived. And so these are my E sub n. These are my allowed energy values for my electron. Now how can we simplify this expression? Well, the easiest thing to do is to look at our original equation right here. And notice that I've got mv squared here, I've got mv squared here. If this is mv squared, there's no reason that I can't just take this expression and substitute it into there, right? That, in fact, I think is the easiest thing to do. So do that really quickly and simplify this expression for E sub n. Pause it and do that. All right, so I've got negative K Z E squared divided by R sub n plus K, or 1 plus 1/2 K Z E squared over R. That's kind of interesting. If you look at this, I've got some stuff, negative some stuff, plus 1/2 of that same stuff, right? If you call KZE squared over R sub n x, then I've got negative x plus 1/2 x, right? 1/2 x minus x is just negative 1/2 x. And so that's just negative 1/2 of this stuff, KZE squared over R sub n. And so these are my various E sub n, but I've already found my R sub n. So take a second, look up the formula that we already derived for R sub n, plug it in, and simplify. Pause. Do it. Okay, so I think the easiest thing to do is to just, we know our R sub n, so this is KZE squared. I'll just take the R sub n that I derived before, flip it upside down since this is on the in the denominator, and put it in brackets right here. I've got an h squared. I've also got a, I don't remember this one off the top of my head, so I always have to look. I've got an n squared. And on the top, I've got a 2 pi squared, I've got a 4 pi squared. A 4 pi squared mk e squared z. All right, yeah, I know this is messy. So I've got a minus 2 pi squared mke squared. Actually, no, I've got a k squared now. Mk squared, because I've got a k times a k. I've got an e squared times an e squared. That's an e to the fourth, right? And I've got, on the bottom, I've got an h squared. Keeping everything involving z and n on the outside, that leaves me with a z squared and an n squared on the bottom. So let me double check, make sure I got that right. All right, yeah, that looks right. Again, everything in this parentheses right here, this set of parentheses right there, is just a constant. You can plug those numbers in and get an energy in joules, and if you convert that energy to electron volts, you find our well-known 13.6 electron volts for that number. And this formula I gave you too, so negative 13.6 electron volts, z squared divided by n squared. Okay, so I wanted to take you through that algebra exercise, which is really just some applications of things that you've already learned in physics, but it is kind of algebraically intensive. So again, if you miss some pieces of that, you should go back through it and make sure you understand them. And I'll ask you to apply some of the implications of these formulas in the pre-lecture questions. All right, bye.